Thanks everyone for attending. I want to introduce Dr. Kimon Simonitis. Kimon and I have been colleagues, friends, and all kinds of things. I knew him when he was a PhD student, and then when he was a postdoc at WPI, I was semi-joking with him, and I said, "Hey," I said, "why don't you get a real job? When are you going to get a real job?" And well, he said, "Why, are you going to hire me?" And I said, "Yeah." So he came to work for me at Victaulic, and worked for me at Victaulic for quite a few years. And he was out of school, and he learned, we ran kind of the advanced R&D group there, process technology. And so we were, somebody said, "Oh, you can't do that." Okay, we'll figure out how to do it. And so we went down that path, and then he had an opportunity with a startup in California, and that's what he's going to talk a little bit about. And this presentation is really, I guess, from a technology standpoint, it really pushes the state-of-the-art of 3D metal printing. A lot of people think, "Oh, I 3D print it and I get the finished part." Well, that isn't so. You've got all kinds of support structure typically. The technology that Kimon was predominantly one of the inventors prints it without the structure. So, without further ado.
Thank you, Jim. Thank you. Good evening, everybody. Test. Do I need this?
Test better?
Yeah.
Okay, thank you. Thank you very much for the invitation. Thank you, Jim, for the introduction. My name is Kimon Simonitis, and today we're going to talk about a little adventure I had in my career. As Jim said, we worked together 2010. He actually hired me in the middle of the recession, so I'm very thankful for that as well. And about 2015, I received a phone call from a guy in California that I'd never met in my life, and he's like, "I'll give you a lot of money if you come here and help me build a 3D printing startup." It's like, "How much?" "This much." "Okay, I'm coming." So I tell Jim, "I have to go, man. It's a lot of money." "How much?" "This." He's like, "Yeah, you have to go." So we parted ways for a while, and after 2 years there, I did what I had to do, and we finished the R&D. Started making products, so the company started becoming more of a manufacturing than an R&D group. And me and Jim, we joined paths again, and we worked together for until his retirement. So this is the story of Velo3D through the eyes of employee number 6. And when I left, Velo3D was about 70 employees and was on the road to become very successful. So we'll talk about the technology of 3D printing, what that specific technology was about, a couple of the patents that I made and how they made a big difference. And I have also a lot of the parts that are in the patents there, all those first prototypes. So very happy to share this with you. So I'm from Greece, and I came here for my PhD. Material science in WPI. I did aluminum and casting. That's where we met with Jim, and I was working at Victaulic, and I went to California about 2015. So the next picture is the day I left, actually, Pennsylvania to go to California, and surprise, this picture is my friend right there, Tim. That was the day we're leaving, and what you see here in the U-Haul is my wife, who was about to be my wife at the time. And this is my SEM, scanning electron microscope, because who doesn't have an scanning electron microscope in his in a one-bedroom apartment? And the reason I had one is because Jim wasn't buying me one. Every year it was like, "Oh, we have a recession now, we'll see the next year." I was like, "Come on." So I went to Iowa, and I got theirs when they were decommissioning it. So, and this is a very beautiful United States there, Colorado. We actually drove cross country. It was a great trip. So when I was at Velo3D, what was the subject there? We wanted to build a 3D printer, right? A metal 3D printer. Specifically, a powder bed fusion 3D printer. And there is all sorts of 3D printing. If you have any questions, I know most of what's going on in the space. But this one specifically, just give you a brief introduction how it works. You have a piece of metal, which is your stage. You put a very, very fine layer of sand on it, 50 micrometers. Well, when I say sand, it's the metal, right? But think about it as sand, it's so fine. And then you just shine the laser and you do a micro weld on a layer, on that layer. You drop it down 50 micrometers, you put another layer of powder, you repeat, so you slowly micro weld your way up. And that's the process. And you can make some very intricate pieces that, I'll show you here. So very fine things, great for high-end, very complicated stuff, and things that casting process would struggle very much to achieve. So I entered pre-series A. For those not familiar with startups, a startup starts with some seed money that someone trusts you, right? Let's say one of you had an idea and you're like, hey, I need $1 million to try this idea. You go to an investor, they give you what's called angel funding, which means it's a bet. I may lose it, I don't care, but take it. And then the moment you prove something, you go in Series A. That's when you exist as a company. Before that, you're in your garage, your basement with someone else's money, with no certain future. So I joined right before that. That's the highest risk, but also the highest reward, because you start getting shares at the bottom, right? So when you exit, you get a good payout. I did a lot of patents there, and we raised about $60 million on Series A and Series B, and I'll show you the parts that convinced people to give us that money. It's very exciting. I was, how do you say it here, bottle washer,
Bottle washer.
that guy. I was doing everything. And again, multiple patents, which we'll discuss. And here's the final product that came out of there. All right, what you see right here, this is the door. You open the door, and inside here is the chamber, lasers on top of the chamber, and the build plate is right here at the bottom. And as you print, it keeps going down, 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 and then comes out, you take your part out. And I'll show you some more cutouts of this. So why is 3D printing important, right? Why? We are casting things just fine since 5,000 years ago, but it adds value, right? What's the value that it adds? One is design freedom. For the first time, complexity is free. You can do whatever you want. You can design it and you can make it. You don't have to think that, how am I going to make the pattern? How am I going to make the positive? Do I have undercuts? Do I need a core? How am I going to support the core? How am I going to get this? All these things, it's a headache for everybody. Here it doesn't matter. You just take a kid out of school, they design something, they don't have to know how it's going to be made, the machine will make it. Of course, you have to understand some rules, but it's a great freedom that it gives you. Fast iterations, no need for tooling, no need for molds. You dream of something, you design it in your SolidWorks model, next day you have it printed. That's it. Supply chain. You don't care if it comes from somewhere over the world, you don't care about stuff. As long as you have the raw material, which is powder, and the machine, you can make it, right? Imagine, and here's one of the pitches that you used to say. You go to people and say, how many ships does the US Navy have? 1,000, I don't know. How much metal do they carry? How many parts? They have foundries in those ships, in the big ones, because they have, if a gear goes down and breaks it, they cannot stay in the middle of the ocean. They have to make it. So they carry all those patterns with them. What if they just had one machine and powder, and they could make anything they want? And that made it a very nice idea, right? And actually, they're very close to doing some agreements now with this type of contracts. Right? No need for inventory. Just need your parts, a library of files, and powder. That's it. And you can make anything you want on demand. So beautiful pitch, very high value. And also performance. You can lightweight things. You can make internal cavities. Everything from the seat buckle on an airplane. Right? Why does it have to be a stamping that has so much metal? You can make it something like this. Right? As long as it's strong enough. And so these are the main things why additive is so important today. where do we see these parts, right? Where do we see parts from this specific one, from this powder bed fusion? Aerospace. All you see here is things that are going, here that's, I think it's an impeller, that's a heat exchanger, a mixer, another impeller, a very high efficiency heat exchanger. So a lot of energy in aerospace. Here's also more energy, like you see all these complicated organic shapes, these super fine heat exchangers, right? And obviously also medical. You can see here implants. This is a titanium mesh, which is great because the roughness allows cells to go and attach and grow on it. Here's hip implants, and this is I think teeth stacked up. If you have any questions, by the way, just interrupt me. Now, talk about the size of the market, right? Because that's the most important thing when you start talking about startups. How much money am I going to make? So this is the overall investment in 3D printing, and it includes everything. The competition here for the products I showed you is between these two categories: selective laser sintering and direct metal laser sintering. They both melt metal, and they are kind of like different names by different companies trying to do a trademark on the method. But see how small the pie was at that time, right? It's this blue area here, and see how big it is today, very high. And here is the Velo strip. They were funded here, 2014. I entered 2015. I exited about 2017, and here they started production. And 2021, they entered the stock market. It was one of the biggest valuations for a technical company, at $1.8 billion. All right. Things happened there. The market, other things, life, overpromising maybe. You're in the rule. The rule of the market. The winds of the market take you whatever. And here they got delisted from the New York Stock Exchange because the value dropped so much. Confidence was lost. And then they were bought by a private company, and now they're listed again on NASDAQ for a much lower valuation. However, when you're a VC, none of that matters. What matters is that you sold the company for $1.8 billion, and that is a huge success. What matters after that, it's not your problem. All right? So
who bought them?
I gotta look it up. It's a private company. But then they put them again, they put shares in the public on the NASDAQ. But it's a very low value. So here's a couple of pictures how it works in general. Here is the build chamber. So this is how you start, the build platform. And this in the beginning is all the way up here. So this is a coater. It starts from the powder reservoir here. This pushes up powder. This pushes the powder over the bed and lays out a very, very fine layer, about 50 micrometers, 100 micrometers. Really hard to get that right with sims and stuff. Then the laser goes and welds your part. It's a micro weld, right? A laser micro weld. That's all it is. Then the next, you drop it down 50 micrometers. You drop another layer of powder. You melt again. You weld the top layer to the bottom layer, and slowly you start building slice by slice your part. It takes a while. And here's how it looks, right? You see the laser here, and it makes lines, it has different patterns. It can do all sorts of things. And this is a single laser, that's how things started. Now, they may have 40 in a chamber.
Question, you're laying down layers. You're going to fuse some of the powder. Don't you have to get rid of the unfused before you move on?
No, you just let it drop down. And it's just there loose. So at the end, you have your part, something like this, that's solid, welded to the stage, and everything around there is a sea of powder, loose powder. And then when you want to take it out, you open the door, and this whole thing goes up, and essentially it rises up like a phoenix, and all the powder just falls down. It's so fine, the powder, it's like a few microns, like 2-3 microns, that it just flows like water. Like the first time I held it in my hands, they gave me a little vial to test, and I did this, and it was literally like waves. It was so fine, like, you know, micrometers. And
So what type of laser are you using? A YAG or a fiber laser?
a fiber laser. This was a fiber. The specific one was a 400 watts laser, and eventually went to a kilowatt. It's challenging. The higher you go, you can go faster, but there's other effects that can happen. Like you have a big melt pool, all of a sudden surface tension may take over and wants to ball up, and you don't want that. You want to have like melt very small pieces, never have it bead, and you know, have a nice control. Because the moment it starts balling, you lose all your edge efficiency. And other things happen. Like the bigger you are, you start sintering the powder around the ball, right? So now it's ugly. It's not smooth. So you have to optimize that. You have to melt just enough to instantly solidify it. When I say instantly, the solidification rate in this thing is about 10,000 degrees a second, right? It's like you see here, the laser is here melting. That's already solid, right? It's just instant. The bead, let's say the melt pool is about 70 micrometers, right? Think about it, a crater of 70 micrometers of molten metal. And you never want to build more than 3 times the diameter as you go. Because the moment you do that, it balls up. Surface tension takes over. So you always want to cool down faster. There's I think Onesorg was the guy that discovered how much liquid you can have as a worm before it becomes a ball. It's about 3 times the diameter. So I found about it experimentally before I read the theory behind it. Yes?
Do you have an inert atmosphere above this?
Yes, great question. So at that time, I'll talk about the players in the field. There used to be 3-4 companies that used to make it. Most of them had what do you call it? A blanket, an argon blanket. They just keep blowing over this area. So this was open the atmosphere. One of the companies were doing it, and constantly you have argon pushing over here, directionally. And directionally is important because you see all the stuff that are flying out here. This is called spatter. So the laser is so strong that in some areas you make like small plasma clusters. That plasma is very violent and starts shooting things left and right. Kind of like weld spatter, but in very, very, very fine scale. Those are, you don't want that to land on top of your metal. That's going to create a discontinuity because it won't melt nicely. It will create a little porosity, a little void. So you always try to weld from, let's say, right to left, and the gas blows from left to right, against it. So all the spatter goes in areas that you have already welded. Yes?
What metals have you qualified this for?
So aluminums, stainless, 316, 304, very standard. Cobalt, chromium, I think, for dental implants. Titanium, several titanium alloys. What else? Maraging steel. The most copper now lately, because they came up with some new lasers blue lasers that could handle the wavelength, the right wavelength for copper, for absorption. So now they make a lot of very fine heat exchangers for circuitry. And the most challenging thing, and I would say a holy grail here, is tool steels, right? Things that get very hard on quenching. So when you make martensite, right? When you quench steel, you make martensite, which is, you undergo a transformation where you have dimensional change as well. So those stresses that you create with this tremendous cooling, they cause movement, a lot of movement because of the residual stresses, and also cracking sometimes, right? Because you have to constrain it, you have to hold it in the base, otherwise it's gonna move on you. But every time you do that, you load stress on the material, and eventually just cracks and can rip the whole plate. It will rip the bolts here if you are not careful. So this plate here is bolted down to the main base, and it's a very thick piece of steel here, of stainless steel. And we see here the support structure. I'll show you more pictures later, but this is an example here of support structure. So I want to make this pipe here. I have to somehow have it sit firm on my build plate. Now, if I don't pay attention and I put too much metal, I can cause this to warp because of all the stresses, and I'll explain the mechanism, and it will actually shear the bolts out. And it may destroy the machine, because all the system that goes back and forth here, back then it wasn't very smart. There were not cameras, there was no AI to tell you, hey, this is abnormal. It was very basic and logical, the approach we had back then. Good. So this is the field back then. Who were the players? There were only 4 players in 2000, in this era here, and that's where Velo started. And the reason why there was only so many players was because of patents. The 3D printing pattern of whoever came up with the concept expired about that time, so that's when people started rushing. Velo was created because at that time, because that pattern was expiring. And only 4 companies. And here's the interesting part, and how is the perfect storm to create a company, right, on such a niche field. Arkham Concept Laser was 2 of the companies, and you can see here how many machines they were selling per year, like nothing, 40 machines per year, and different sizes, right? Like very small. And this here kept going like this. I don't have latest data, but now the field is, we may have like 20, 30 players globally making machines, a whole lineup of machines. These guys now just had 1 or 2 machines back then, like a small one, like this, and a little bit bigger. Now we have machines that are like a cubic meter. They have 20 lasers on top, and they just crank parts, right? It's a very different field. A lot of automation has come in. You asked me, by the way, for atmosphere before. There was a machine that was open air, but the best one that Renishaw was making was pulling vacuum, doing it twice, and then flushing with argon. And the reason was, and this, you guys will appreciate this, the oxygen levels. So when you have a very small melt pool, right, about 70 micrometers, and you want to control how deep and how wide it is, because remember, like you have a part, you cut it in slices, and every slice, it's like a CNC, you have to design a toolpath, right? Now the toolpath, as it goes back and forth, has a distance between the you know, like you move 5 micrometers to the left, another 5 micrometers. If your melt pool is not consistent, right, you're gonna have either over melting or under melting. Both are bad for different reasons, but you have to control that. Melt pool is very dependent. The convection patterns in a melt pool, they're correlated with the oxygen content. So when you, forget the number if it's like 800 or 2000, but let's say 2000. At 2000 ppm of oxygen, the melt pool, instead of being like this, the convection patterns, they go outwards. Things happen, the surface tension changes, and it goes outwards. So instead of like going deep and welding nicely to the bottom layer, you go outwards, so now you don't have penetration. That's going to end up with a layer that won't be adhere very well, and just going to split and separate. So that's why it was very important. And you know, you spend 1 day printing and 3 days hunting leaks. We were running, I sent a guy 5 hours away to impregnate the pump, the vacuum pump, because I was suspecting the casting had leaks. So, you know, every day clean the seals and all that stuff. And if the oxygen was creeping up, you had to stop the build. Like it wouldn't work. It would cause separation. So yeah, very, very important.
What kind of level would you stop at? 10 ppm, 20 ppm?
No, we would, we would know our machine, because it wasn't perfect in the beginning, so it was always creeping up, and we kind of like knew what to expect. So we stopped the build there, pumped down, about 10 minutes took to pump down again, and then start building until you hit the critical threshold where you're going to be near to that level I told you. Here's the interesting part. That was a surprise. That 2016, GE bought these two guys, Arkham and Concept Laser. And these guys are all European, by the way. There is not a US company at the time. There was GE, but they made a piece of junk. Literally, like they recalled everything. It was embarrassing. That didn't work. So there's only European players. So guess who's interested in these things? The Army. The US Army is very interested in these things, and DOE. And they cannot invest in any of these guys because they cannot talk to them. They cannot talk to Europeans. They cannot send drawings and models and have intelligent discussions about proprietary designs. You guys know that much better than I do. So there was a lot of support for a US company to make a machine like that they could go and talk, share, sign NDAs, get in their house, and show them stuff. So that was a very good, let's say, push. And SLM was another German company acquired by Nikon for about 600 million. So that was interesting there because it did what we didn't want. It put a valuation on Velo. And that's the last thing you want when you're making a startup company. You don't want to say a number. You don't want people to think you as a number. You want people to think that you have infinite capabilities, possibilities, infinite as much money as they can give you, right? Something like Tesla, right? So yeah, interesting. Also, Arkham was a different company in the fact that they actually, think about the scanning electron microscope. That's what they made. So they were hitting the whole bed in about, let's say, 800 C, very, very hot. And they had an electron beam that was melting it. And electron beam is so fast. Laser is a physical thing. You have to move galvanometers to move the laser around. In an electron beam, you just have some, it's all electricity, right? It's super fast. So you can have almost concurrent melt pools. And the best thing in those machines is that since everything is at the same temperature, there is no heat distortion. There's no warping. So, but it's an ugly part. It's a very rough part. So it's a niche, but it's a different market.
Is it typical to heat the plate?
Yes, you try to heat the plate, but in metals, so for example, plastics, you want to heat it up very close to, otherwise it's going to warp, right? Today, if you get a 3D printer, the plastic ones, like Bamboo Labs or anyone, now everybody has caught up. You see the plate gets hot, and you can make a big square, which before, 5 years ago, this would be unthinkable. And because it's heated plate, it doesn't warp on you. In this case, it's very challenging because, let me go back here. Here's your base, right? How do you seal here around here? Silicon. How high can you go with silicon? 200 degrees at the best, and hope it's going to last. And how does it's going to act when it's hot and soft and you're moving it against metal and powder? It's very challenging. And so you want to get it as hot as possible, but then that's going to kill your efficiency as well because I have to wait for it to cool down when you take it out and handle it. So tricky. So here is today. There's so many machines, very low cost. This is the Renishaw tool, very high end. This is a Trump. This is a forget the name of these guys. Morris, I think. It's a US company. SLM, GE owns them now. Concept Laser, German company. Nikon bought these guys. GE owned these guys. And that's the Velo, very big printer. You see here how big it is. You need like a ladder to go up and look at your part. So Velo found another niche here. That's why you see it's a very tall printer. Things for space, like rocket engine parts, that they're all round like this. So Velo stage is round, where everybody else is mostly square. And yeah, this, beast machines, very big. So they have a lot of options. And also the overseas guys have entered the market and really, did what they do every time. They, at 1/3 the price, they offered the same parts, and they caught up very fast. I wouldn't be surprised if overseas they sell more and use more than we do here of printers. So, okay, you want to make a company, right? What are we going to do better? So you have to find the pain of this technology. And the biggest pain is the support structure, right? You have a metal. You guys familiar with welding? Right? So when you weld, what happens to the metal if it's thin? Right? It wants to move on you, right? It wants to warp. If you pass a hot torch, right, and you make a metal red hot, and you let it cool down, ain't gonna stay there. It's gonna move. So in order to avoid that, because you cannot print, you have to put supports. You have to support it. And that's what you see here. You see all those pieces? This metal supports. Look at this stuff here. This is a wheel from a race car. Look at all this. That's metal supports. Here, this piece, I don't even know what it is, but look at all this stuff. Supports. Here, this is a nice stack-up. You can let it run for maybe 10 days to make all these things. But look at all this. Support, support, supports. Who's going to take this out? If it's not something that's like perfect flat, right? So you have like a EDM, go and cut it. Some guy is going to sit in a desk with snippets and pop them one by one. And then he's going to get carpal tunnel, and then the next guy is going to go there. Very tough. So the idea was, okay, we're going to make supportless 3D printing. How? We don't know, but that's what we're going to do. So everybody loved it, loved the idea, right? And that's what you want when you have a startup. You want to have a compelling idea, even though you have no idea how to get there. You have to claim you have some idea, but you don't need to know. So it's really shooting for the moon. And when we go over the fence, we clap here. It was very, very ambitious undertaking. So talking to people in the industry, we did interviews. It was equal the time to print. It was the time to remove the supports, right? Yeah, I'm going to pass the part around. This is a plastic part, but you can see kind of like the support structure. All right. So let's see what's next. So again, what do we want to do? We're going to make no supports. Here's a conventional, right? This is an impeller. It's called a shrouded impeller, right? And it has many benefits. But you cannot do it. You cannot do it because there's no way to get inside here and remove the supports. They're not soluble by any means. They're the same metal as everything else here. How do you get them out? You cannot. So you cannot make these pieces. You cannot make floating parts, and I'll come back to that. You cannot make internal cavities. Now we're going to reduce the labor and we make it much more user-friendly. So here is the end product here. This actually works. And what you have is just the bottom supports, right? Which is very easy to remove with an EDM. This is like you just set it on the machine and it goes in and the wire cuts it, no problem. It comes out beautiful at the end. So that's the idea behind it. And it was one of those things where everybody looked at you and you're like, you're crazy. It will never work. You're wasting your time. It was this type of thing, like huge disbelief. This was impossible. Like, there's no way to do this. They've been working with these paints for decades, right? So it takes a little bit of a madman to go against all that stuff, to be arrogant, totally arrogant, right? And not listen to the experts and say, you know what, I'm smarter than all of you guys. I'll figure it out. You have to be, there's no, I don't know what other word to use, like arrogant. Maybe that says something about myself, but you need to have some of that craziness. So here's why you need supports. Here's what happens when you don't have supports. This is test pieces. You see your capabilities. So what we see here is we're building, here the supports to the build plate, which is right here. And this is a test. So this part, you angle it 50 degrees and everything looks fine. 45 degrees and looks fine. 4 degrees and you start seeing the ugliness here. Very bad roughness. 35 degrees and it just gets worse until 25 and it's just destroyed. Right? This is not sustainable printing. You cannot print this. Same thing here. This is an example of overhangs. This is a 100 thou, 300 thou, 500, and you can see here these droops. We call them stalactites. All right, it's like stalactites. Here's an attempt, and this is like very small here. That's 3 millimeters. That's 100 thou, right? 120 thou, 3 millimeters. It's nothing. And you see, you cannot make it. Look at this roughness here. You cannot trust you'll finish this print. Look at this, horrible. Same thing here. You try to do these things, very bad. Why it happens, right? Why does the stalactite happen? And this is where everything starts. So imagine you're printing something at an angle, right? Let's start with the vertical. You print the first layer here, and this is my wall. I'm gonna put the second layer. When the laser comes here, and it's gonna melt the top, what's underneath? Metal. The heat is gonna get sucked by the metal, and the powder, and the melt pool is gonna just stick here just fine. If I push out, now I'm melting this area, underneath here is just powder. The same laser energy that made a nice melt pool here, that attached, and the heat got sucked by the main piece, that same energy has to be absorbed by the powder. Powder doesn't have good heat transfer. It's like air, actually. So that energy is gonna make a huge melt pool here, that's gonna make a huge droop. It's gonna attract powder from the vicinity, and you're gonna end up with a big ball right there. And now repeat this across the whole line and going up. That's what you see right there in the droops. So that was the big problem. It's like, how do we solve this? That's like crazy. So the industry knew that about 45 degrees, and that was the recommended. After that, you need supports. Supports will take the energy out, will hold it together. It won't be nice, but it will be there. You know, when you remove the supports, things are rough, but at least you won't destroy your print. Now, here's the very interesting thing. You guys will appreciate this. Why does it warp? And when I discovered this mechanism and I spoke to the CEO, he actually stood up and left the room. He said like, I don't agree with you. He left. I was like, I'm pretty sure that's how it works. So warping is the other half of this. So droops, they're very ugly, but what's most dangerous is the warping. All right, so what happens here, if you just follow this logic. So let's say you have this piece of metal here, it's a block, and you shine your laser here, and you melt something on it. You don't have to melt it, just think about it, it gets hot. What happens? It expands, right? When it expands, this area gets under compressive stress. When this is compressive, what is this? Sorry, tensile. This is compressed here. It's a spring, because you push out here, and this gets, it's a spring winding up. When you keep heating it up, what goes down? The yield, right? At some point, when it gets close to red hot, the yield goes to nothing. When you melt, there is nothing. This here is a spring. It's waiting for you to get out of the way. And when that happens and you melt this part, this spring throws everything back, and that's what you're at. You end up with a warp, right? That's warping. And if you don't warp, trust me, you have yield stress, you have stresses there that are very close to the yield, right? And every weld guy knows this. And this is the effect of this. You have so much warping that, this is an aluminum alloy, I think, that you just rip yourself out. It has so much power, it will rip itself out of the build plate. You can see here, these are tensile bars, right? And how they just separate because of this mechanism, the TGM. So these two things, the drooping and the thermal gradient mechanism, is what stops the progress for 3D printing at this moment, right? And everybody is made peace with it. It's like, okay, well, it is what it is. What can we do about it, right? So, how bad is warping? Warping is just destruction, right? So you try to make something at an angle that's thin as well, right? And the red here is the height of the build plate. And you see here they're trying to make a bridge, just goes up and raises. And now you have stuff sticking out of the powder bed, right? If those things are higher than 50 micrometers, which they will be, you're done. The way I say that. So this blade here, the roller, is nothing but a thin silicone wiper, very soft. When this thing sticks out from a bed, the wiper goes over it. Guess who wins, silicone versus metal? The metal, thank you. So what happens? The silicone here creates a little void. Mm-hmm. What happens when you have a void in your wiper? There's a nice mountain of powder getting left behind. Well, that powder is going to get lazed, and it's going to be even higher now. And that higher spot is going to hit this and this again, again, and again. And if you forget your print overnight, you're going to end up in the morning with the metal eaten away. And that's what happened the first time we noticed that. We went back in the morning, and half the wiper was gone because it was keep grinding against the metal. So it's a self-destructing mechanism. So that's what happens, and you lose a lot of money here if you lose a print due to the warping mechanism. So how do we solve these two problems here, right? So these are the two main innovations that we did at Velo. One was a contactless vacuum wiper, and I'll explain why this was important. And second one, we thought in 3D instead of 2D. What I mean in 3D, when everybody was slicing each layer and making the print patterns for the laser paths for each layer, they were not thinking what was in the layer below and the layer below that. It's just, whatever you made, I'm lasing it. So you didn't take into account what was below that. Or you were not playing in a 3D. You just, had that 2D canvas every time. And that was what gives us another dimension to work with. So first talk about the contactless vacuum wiper. So this is important here because you want to have no supports. Well, you're pushing metal powder, right, over your part that's floating. Well, this is like water. It has the consistency of water when you push it. You're going to move the part, and then you lost it. You don't know where it was. So it's important to not touch it. Also, when you have something going vertical without supports, and you keep pushing it, it keeps bending and bending and bending. Also destructive. So it's very important to not touch the part. So this here was the first contactless viper in the industry. It took us a lot of time to develop. Now there's another company, DMG Mori, that made one that's ultrasonic. I'll explain that. So here, the way it works, instead of like having just a silicon blade pushing here, you have all this device here. So it goes from right to left. And number one, here's the previous layer. That's the dotted line. Number two, here's the powder delivery. So you put a thick layer of powder, very thick. I said the layer height maybe 50 micrometers. We're going to put 300 now. So this is like 300 micrometers. Second step, because you're dropping it, is this kind of like free falling. It is not flat, right? So we put a viper here. So we call it longer range viper because this is still like 200 micrometers now. But it's flat, it's consistent because you hit it with a hard viper. Our parts are deep here, right, deep down. And then at the end you have a vacuum that you suck the excess powder off. And that took a lot of tuning. And here you can see all the patterns of the different layouts. You had small holes in the middle, we had high suction, bigger holes here, we had a linear one. We tried many methods to have a uniform vacuum line. But that's how we did it, and we didn't touch the parts on the powder. So that was the first big innovation here. Again, much more complex system. Like here we are really making our life difficult, but that's the only way to enable this innovation, right? From going from just a silicon piece that you just buy $5 from McMaster to a very complicated here, finely machined device that pulls vacuum. And you have to care about the nozzles clogging and all that stuff. Yeah, I'll show you in a minute the first part we printed thanks to this.
Is the powder always at the same size, or did you have to vary the vacuum depending on the powder size?
Yes, correct. You have to change the recipe depending on the material. And powder size, you can change it. What will affect is how fine of features you make. I'll show you some parts here that have like internal channels, for example. You want a fine powder. But it's not straightforward, you have to develop it. It's not like I'm gonna change the powder a little bit smaller, tune a couple buttons. It's a whole process of qualifying all the different building parameters, right? All the different building blocks to tune the laser, tune the paths, tune the bander layers, all that stuff. But yes, and the powders also, there's a lot of science there as well. They are not uniform distribution. Sometimes they're bimodal distribution because they flow better. Right, so it's a whole science behind those.
Well, I assume the vacuum had to change depending aluminum versus what,
Yes.
316.
Yes.
Lighter. Okay.
Correct. All right, so what this enabled us, this is the first success year. And I remember the happiness when we got this done. This is a free-floating cage with another innovation here. I'll talk about it in a second. But it's a free-floating piece with a ball inside, totally supportless. And the baby part, don't squeeze too much. What's the first one? And here's a little square. When this happened, we acted like we won the Super Bowl. Right? And it's very cool because you're printing for 2 hours here. You don't know what you did because it's buried. Right? All you see is every time is a laser shining things on the surface and you hope that it's there. And then you open the door, you put your hand in the sand, and you're like, yeah, it's out there. You know? Big moments come from small things. Now, here's another challenge you guys are going to appreciate. Imagine now you have powder. Powder is not dense, right? It's mostly air. What happens when you melt a piece of powder? Overall, it may occupy a space like, let's say like this. The moment you melt it, it's probably 1/3 of this. What do you do with the rest of the volume, right? Think about now you make a line, right? That line, let's say I melted 3 inches of metal. Well, it's not 3 inches when you melt it, it's going to be smaller. Okay? Let's say now I want to make a circle. How do I connect the beginning to the end of the circle if there is no powder there? Because there won't be powder. The first hit, it's going to collect all the powder and you end up with a gap. All right? We call it starving lines. Right? And all has to do because the first hit, you suck most of the powder around it. There's nowhere for the energy to go. So you suck a lot of powder and you create a little gap, a void there. The question is, how do you go back to the same spot? Like there is no powder there to complete it, right? If I had to do it, it would be like a ring, and at the end of the ring, it would be like nothing. I would just melt the powder below and it would look very ugly. So how do you solve that? That was a lot of learning first. I was like, where's the powder? Why doesn't it do it? How do I connect, this piece to this piece? And we started printing in pieces. So here's layers. So this is the first layer here. And you see we don't make a wire, a continuous wire. We make pieces of the wire and we leave control gaps. And then we have what's called the healing layer. We add more powder on top and we connect that. And that was much easier to do that. We got even better at that. And here's another concept where you can see it's like playing Legos. But the thing is that every time you do this, so when you do this layer, you have a gap here. There will be a gap. You put powder, now this is filled. Right? So there's powder up to here, and this area is filled. And now you hit it from the top, and you make a nice solid piece. So there was a lot of these little details that you got to work with. Talk to the software guys, which it was a great thing because they were right there next table. They were like, hey, I need you to do this. Go make the software, give it to the application guys, they put it on the machine, and then you're like, okay, this is going to be what we're going to do now. Execute. And we did it and see what happens. So that was a lot of fun there. And here's where the honors work number, I learned about that because I wanted to go fast here. And I was limited by how fast I can go because of you cannot make the melt pool more than 3 times your diameter. So that limits how fast you can run the laser. This is the warping now. All right, so we figured that part out. How do we deal with the warping? And here's the first attempts. They're all ugly. And I gotta say some of that was my ideas. Here's what happens, right? So you put the first layer down. The moment you put the second layer on top, this warps up like that. And look at this, how it makes a U shape. This is supposed to be a cube, a perfect square cube. And no, it makes that. And it's ugly. Again, in big pieces, this is actually force that's pulling it up. And we came up with many ideas. We're like, oh, let's put ribs on it. Ribs are good. Ribs stiffen things. Well, those ribs were warping everything as well, right? So nothing was working, but in a pattern we're like, you never know, it may work. Just put everything there. So these patents are like 120 pages long. So yeah, this is like different building blocks. So this, for example, is a sheet, and here is ribs that go into the wall, and we're thinking that, you know, we can give rigidity to this. It wasn't the case because it was warping the other way now, going up like that. So hard to win. What's going on? So that was the TGM, the thermal gradient mechanism. That's what was causing things to warp. I got so good at this, at the warping mechanism, that I could make this like as a raffle chip, right? These waves, they're all controlled. And the way you used to do that is by controlling which way the metal will bend. So I could make it bend concave or like this, right? It all has to do with the laser pattern. Later I found out that they actually use it in when they bend sheet metals with lasers. So the laser, the metal comes out, and you can run the laser like this, back and forth, and it makes a nice curvature without tooling, just by heat. You can even do it with plastic, right? You can even take a bottle, well, not this one, but if you heat the bottom up, now this one is very weird here, but if you take a plastic cup and just put some heat on it with a lighter, it's gonna pop up or down. And that's kind of like the basis of the thermal gradient mechanism of what happens. So here we thought, oh, you know what? Kimon can warp it this way or the other way. Maybe we can pre-warp it. And then it's gonna warp back to itself. And so that was the idea. So this we know it doesn't work because we're gonna warp all the bottom layers. And then we're like, well, if we do it like this, maybe it's gonna fix itself. You know, we build one layer warped like that, and then it's gonna go back to its place. It kind of worked for very specific things, but it was a disaster. It was physically impossible to do that. The trick to warping it the other way, away from the laser, is to have a huge beam, about 4 times the diameter of your part. So the thicker you become, the more impossible it gets. So how do we fix it? The truth is that the TGM, the thermal gradient mechanism, had different, it was explained mathematically how it worked. And there was only one variable that you could control in it, and that was thickness. The thicker you are, the harder it is to warp. All right, fine. How do we get thickness, right? I can't get very thick because I get stalactites here, and I get, and they get destroyed. How can I do it? I got to get rid of the stalactites first before I give thickness. And then I'm under the gun now because it's my time to shine, right? It's like we're waiting for Kimon to figure this out. And there's 20 people that are waiting for me now to figure it out. And I'm like, I remember I'm on this whiteboard, and I have this, very young engineer with me, just looking at me, kind of like hoping I can come up with something. So I'm looking at the stalactites, and I'm like, why? And I start asking why. Why is it drooping? It's like, well, it can absorb the energy, the powder, and it makes a droop. And I was like, oh, it makes a droop, so it droops. What if I catch a droop? How can I catch the droop? And that's when it started. I said, droop, catch it. How can I catch it? So there it is, and this is the mechanism of catching a droop. Here is a very fine layer, very thick as well, 650 micrometers. It's very thick, right? Remember, each layer is 50. And you can see the bottom. It's perfect. It's better than the top, almost. So how do I catch it? So here, you see the black. So this is multiple layers here, right? But let's say this black layer, this is not fully solid. It's just sintered metal. All right, so then, after I sinter the base, and you see here, that's the overhang, right? So I can go out here, I add more powder on top of it, and then I melt. So the sintered metal underneath now my layers will catch the bead of the metal, the melt pool. Not only catch it, but you have a preform essentially. It's going to wet beautifully around the sintered metal, right? Because it's just balls, but they're welded together, and it's going to wet beautifully. And it won't droop, it won't go anywhere. And that's how it happened. It was just a simple thought. And
But how is it sintered? You mean you're using like a lower power beam?
correct. Correct. You can adjust the beam wattage, focus, speed that you're going, anything. So, yes, exactly that. Exactly that. That was the first 3D printing of metal was exactly that. They didn't have strong lasers. They couldn't control any of these things remotely close. So they used to sinter everything. You have a sinter part, and then you go and same as sinter metal today. Now, Jim gave a presentation of that. But you could start with a very complicated green form. So yes, exactly that. So the black area has like a sintered structure. On top, you melt it, and then just goes and wets it beautifully. I'll show you a part right now, and you will see the bottom of it. It looks better than the top, right? And this here was unthinkable that you could make. Remember what I showed you before here with this like a 30 degree and just gets destroyed. This is like 5 degrees, and the bottom is totally droopless. So that was a very big breakthrough. I actually remember when I presented my thoughts here, nobody believed me it's going to work. Totally not, nobody. But I was so excited that they called me even a cheerleader on that meeting. And then we did it, and everybody was like, what's going on? How does it work? So like this was totally unheard of. Like the normal thing at that time was this. Like this was our daily life, this disgusting thing here. And that was there, amazing. Like you didn't even have to finish the bottom. So this enabled us to make parts like that. And this came from space companies. Here, these were test parts. And they were like, if you make these parts, it's very high chances we're gonna buy your printer. So right now, SpaceX has bought many of these printers, right? Because they are the best to make this type of parts with no internal supports here. So this technology enabled these two types of parts. And what you see here is an impeller. And you can think that when you slice this, you have many angles here that are less than 45 degrees. And this technology enabled that. And what you see here, that's one of the parts from the batch from that small one that I passed back there. And here's the idea. You see that black layer here, that's the sintered metal layer, right? And that's the build-up on top here. And where's it? The part you see here, it's this. And the small one is this, right? In the patent. So here you can put them around. Very, very exciting times. You know, it's from those very small thoughts. You know, you ask the why, you use the language, and somehow it comes on you, right? The answer is always there. As Socrates said, it's like we were born with the answers, just need to remember them. So, yes. So these were and that's what you hold the two pieces there, these ones. That's one that got the Series B and really launched the company. After that, it was a matter of execution, of getting the manufacturing right, get the right size of platform for the customer, and packaging everything together. And that was it. That was really the launch of the company. Now, here are some parts that this printer can do, others cannot. These heat exchangers, these tall vertical walls, they're impossible when you have a wiper, because a wiper keeps massaging them, keeps pushing them. And the taller you are, the less rigid you are. So it's very easy for the wiper to push it out of the way. So this is only possible without any supports, right? With this printing technology. This is another one, shrouded impellers. These are great because you reduce the leakage. They're much more efficient because you don't have leakage, right? When you have a regular impeller like the one I just passed, that impeller, the walls do not match the housing. So you have leakage of liquid there, so you have a lot of waste. These ones, the liquid goes from one side and just gets pushed from the bottom. There's no need for a housing. It's beautiful. But you cannot make them if you don't have supportless printing, right? So this, where is it? There you go. This is a very good example. Of the application of this technology, right? So this is how the niche was found, right? Because everybody makes parts, but what's your niche? Why should we prefer to buy your printer? Well, because you want to make these parts. You want to be competitive, and when you're in space, you care about everything. Every gram you can save, every efficiency you can squeeze out. Pump housings, right? All this is an internal channel. Well, you cannot make this if you don't have that technology. You have to cheat your way around it. How to cheat your way? Instead of making it like a tunnel, you make it a pyramid. Put a 45-degree angle. And then you meet the top, right? That's the only way to make a ceiling here. But with this technology now, you can have a nice shape here, like a normal pipe. And this is kind of like one of the, this is not Velo, but it's another company, and they have 20 lasers. At that time, we started with one, right? Now the technology, after 10 years, we have machines that have 20 lasers and 1 meter cube powder bed. Technology has been so reliable now that people can do that. And Velo has patents on these things, and it took a while, and I was very surprised that people, how can I say, talk about arrogance before, that you need arrogance to come up with a crazy idea, follow it, and beat the guys that are in the field with the technology. But it's amazing how arrogant the big guys are as well, and they don't look at you. They don't look at your comic. When I went back to Victolic with Jim, I went to see the latest Rennie show once, and I was like, do you know who I am? I spoke to the guy for the 3D printing, the manager there of the R&D. It's like, no. So I haven't read the patents from this company? Oh, I've heard about it. No. It's like, they're coming for you. Just so you know, they're coming for you. What do you mean? So eventually they caught up a long time later, like maybe 5 years after the Velo made a printer, people started understanding what's going on and how they were starting to eat their breakfast. And it was amazing how arrogance can drive you to do something, that nobody else thinks is doable. But also, how can it make you blind on the other side, on the guy coming from the rear view mirror that wants to take a piece of the pie from you. Here I have a couple other cool 3D printed stuff. So, just general 3D printing talking, you've seen 3D printers for homes that put clays. This is a very interesting one. This is the biggest 3D printer, and it's actually a TIG, MIG actually, a MIG welding head at the end of the robot. But this makes actual parts for space. So this is a satellite component for a gas reservoir. Very impressive. This is actually in production. And this is a big here, a big rocket. And this is called Relativity. There's a company in California, and that's the 3D printer. And it makes huge parts, and again, it's a welding head on a big robot. But they have controlled many things, and they can do big stuff. This is another company that we work with them as well. This is the engines, multiple engines, same as SpaceX does. And if you could zoom here in the picture, you see that everything here that I'm pointing, everything metallic, everything is 3D printed. Everything. So, that here the impeller, the pipes, the angle, this piece here, the nozzle, everything. So this is the Electron rocket there from New Zealand. And, last year, this is another piece of technology where Velo excels because of the technology to make very fine wire meshes. And see here you have, today with the CT technology, MRI, where you can scan someone's body and understand in 3 dimensions where his bones are and what's missing from someone's skull. Look at this guy there. He's still happy even though he's missing half his skull. And they scan it, they go in the computer, they make the mesh, they 3D print it in a night, overnight, right? They send this guy his titanium skull. He's happier than before. Somehow he has hair there. I need to know how that happened. And amazing, right? We live in a great times here. And that's it. Thank you very much for having me here.
Thank you, Kimon. Kimon traveled from Pennsylvania to come and do this show for us, this presentation. So again,
Thank you, Jim.
thanks. Kimon's actually a partner in 2 of our businesses, so he's going to work tomorrow in our factory here. Any questions?
Yeah, how long has your, okay, 2 questions. One, it looks like you're controlling the melting cycle very carefully, temperature, power, to overcome the warping problems that you had. That's a software approach to solving the problems. Are your patents for the software?
There is, no, I think that's a lot of trade secret there, because you don't have to tell them how to do it.
Okay.
But what you just said about the controlling of the melt pool, that was very critical. And it has to happen very fast. So the way we do this is we actually, so the laser comes, right? And there's a split mirror here that transpires whatever comes here this way. So it goes here, it goes to Galvo shut it down, but the light comes also up, right? So that light goes back to that split mirror. It doesn't go back, but it goes up, and there's a pyrometer there. And we actually have tried many things. We have a camera that looks at the size of the melt pool in real time, and also a temperature sensor. So with those 2, we can react very fast. Like we have to use a FPGA. Essentially, it's a computer that we are programming to the core, because you cannot have Windows handle this process, right? Lasers and galvos and such a fast movement. Because the laser moves at 7 meters per second on the build plate. It can so fast to have. It transfers so fast. You go much slower when you print. But yes, that's how we're controlling the size of the melt pool. Because if it runs away, then it's just you can warp, you can droop, you can lose your print.
Joe, you had a question.
Yeah, I mean, a rough surface is nice, but what if you want a smoother surface? Do you use smaller powder, less laser energy? Can you get a smoother surface?
Yes, so you can, at the expense of time.
Right.
The way you do this is you can remelt. When you remelt the layer, or your, let's say the periphery, right? You don't have to remelt everything. You can get it very smooth, because you don't deal with powder at that time. You just deal with solid metal that's a little bit rough. So you melt it locally there, and the surface tension takes care of the rest. When you have powder, then that's, powder doesn't have good heat transfer. So it just likes to soak, attract powder particles, but the moment you melt, you actually create a trough between the powder and the metal. Because you melt the powder, and it pulls back away from the rest of it. When you remelt it, it becomes beautiful and shiny. So yeah, that's how you do it. But to get an underside very nicely, you have to do these tricks with that I explained before, with the sintered area first, and then a remelt on top. So that's how you do it.
Just so you know, that's Mr. Laser Welding back there, so that's asking a question.
Oh,
So maybe he'll show you some of
Maybe.
his tricks.
I wish I knew you earlier. You could have answered my questions.
We had some of the first lasers made here at the facility when we were DOE.
Oh, that's great.
We weld explosive components. So we needed the very, very low heat input,
Mhm. Yes.
high power density, low heat input.
Yep.
So yeah, we had serial number 1 for some of the lasers.
That's great. That's very cool.
Oh,
Yes, sir.
You were talking about the part is on a base that retracts as like a piston,
Yes.
and you use a silicone compound for sealing it. I mean, if you use the stainless steel bellows or something like that, you could have much higher ambient temperatures for watching.
I wish I knew you earlier. That's a good idea. We didn't think about that. Yes.
I mean, in semiconductor processing, for example, a wafer is put into a chamber remotely and it sits there, and then they move the chamber up, and there's bellows that takes up the motion. And that's something you could borrow from their industry.
Well, that's a great idea. That's a great idea. That would help a lot. It's still a problem because, keep trying to push the envelope with other alloys. You need higher temperature. It just makes your life easier.
Yeah.
And the limitation is right now with the sealing. Also has to be a vacuum seal, right? An atmosphere seal, what you're making there. But I think the bellows would work great.
Yeah.
Well, thanks everybody for coming.
Thank you, guys.